I'm Kumar. Our work studies the problem of recognizing apparent emotions from speech data in cross-cultural settings. This problem involves learning a function that can map segments of a speech signal to points on a continuous two-dimensional space composed of valence and arousal axis. Why is this a challenging problem in the first place? We argue that fundamentally, the processes of vocal emotion, expression, and perception are highly subjective in nature. As a result, the ground truth labels of emotion are influenced by various subjective factors. In cross-cultural settings, this challenge becomes even more severe due to factors like language-specific tonality and so on. Due to all these factors, an emotion recognition model must have the ability to accommodate such a wide range of intrinsic variations effectively. Existing methods for cross-cultural emotion recognition apply techniques like domain adaptation, transfer learning, and meta-learning to models like recurrent neural networks or its gated variants or one-dimensional convolutional neural networks. These methods achieved impressive generalization performance on challenging databases. However, it is important to note that all these models pose emotion recognition as a purely deterministic regression problem, in which a single mapping function is expected to cope with all the aforementioned variations in speech emotion data. In this work, we hypothesize that such deterministic regression models may not have enough representation capacity to accommodate the wide range of intrinsic variations. And we argue that a distribution over temporal functions could be more effective than a single temporal function for speech emotion recognition, particularly in cross-cultural settings. Here, we make the following assumptions. First, the relation between speech signals and their corresponding emotion labels is governed by some unknown underlying stochastic process. Secondly, each labeled sequence in a speech emotion recognition corpus is assumed as an instantiation drawn from the underlying stochastic process. In deterministic regression models of speech emotions, the training process outputs a single temporal function, and at test time, the same function is applied to any given input to predict the emotion labels. Whereas in stochastic process regression models, the training process outputs a distribution of functions rather than a single function. And at test time, given a specific input signal, we can first condition the learned distribution on that specific input to draw a function instantiation. This method provides the flexibility to sample different functions for different inputs at test time. For stochastic process regression, Gaussian processes are the most popular methods in machine learning literature. Some existing works already explored applications of GPs to speech emotion recognitions. But general GP implementations have two important limitations. First, they require handcrafted kernel of covariance function as input. Second, GPs are not easily scalable to high-dimensional feature spaces. Addressing these limitations, neural process family has emerged as a promising alternative to GPs. NPs combine the best of both worlds: representation learning capacity of deep neural networks with the test time flexibility of Gaussian processes. In NPs, given a sequence of input target pairs, first we sample a small set of input target pairs as context points, which we use to infer the distribution of a latent variable, representing the function distribution we are aiming to model. Then a sample drawn from this latent variable distribution is used to predict the labels of remaining points in the input sequence. Most importantly, in NPs, we don't need to hand design the covariance or kernel function, unlike in GPs. Also, NPs are linearly scalable models, unlike GPs. In terms of network architecture, NPs are very similar to variational autoencoders, using an encoder-decoder composition with the bottleneck layer modeling the latent variable distribution. To leverage such interesting properties, we propose to build a speech emotion recognition model based on neural processes. However, we found that direct application of NPs to speech emotion recognition is not a very effective approach, mainly because the static encoder-decoder modules used in current NP implementations require a perfect temporal alignment between the speech signal features and their corresponding emotion labels. But temporal misalignments are naturally present in speech emotion data collected in the wild settings. To address this problem, we propose to replace the static encoder-decoder modules with temporal encoder-decoder modules. Secondly, NPs require ground truth labels for the context points at test time, which is not practically possible. To address this problem, we use proxy labels in the place of ground truth labels in order to infer the latent variable distribution. Here, the proxy labels are noisy predictions made by an already trained deterministic regression model. With these key changes to the base NP model, we formulate an alternative method to stochastic process regression using NPs. The objective of this method is to model the hidden or latent variables of speech emotion data as random variables drawn from some underlying stochastic process. For this purpose, we aim to learn a model in which an emotion label is a function of not only the speech signal features, but also a stochastic latent variable. Here, this latent variable is drawn from a multivariate normal distribution, which is an instantiation of the underlying stochastic process. In our model, given a sequence of feature vectors, to predict their corresponding emotion labels, we use three key models: a backbone model, an encoder model to infer the stochastic latent variable, and a decoder model to predict the final emotion labels. First, the feature vectors are passed to a pre-trained backbone model, which is a deterministic temporal regression model that predicts the proxy labels. These proxy labels paired with their feature vectors are passed to the encoder module to predict the latent variable distribution. Here, the latent variable distribution is parameterized in terms of its mean and variance vectors. Finally, a latent vector drawn from this distribution is used by the decoder module to produce the final emotion labels. In the implementation of our framework, we first extract the features from an input speech signal. Then these features are passed to the backbone module, which is a recurrent neural network, to predict the proxy labels. Then the features and proxy labels are passed through their corresponding embedding networks. Using their outputs, the encoder module, again a recurrent neural network, summarizes the context into a joint embedding, using which we predict the parameters of the latent variable distribution. From this distribution, we draw a latent vector. Finally, the decoder module takes this latent vector as input and combines it with the input features to predict the final emotion labels. To train this model in an end-to-end fashion, excluding the backbone model, we used evidence lower bound objective function as the loss function, similar to the training of neural processes. To validate this approach, we trained our models on an in-the-wild speech emotion recognition dataset used for AVEC 2019 CES challenge. To investigate the effectiveness of our method, irrespective of the speech features used, we trained and evaluated all our models using three different types of features: one set of deep learning-based features and two sets of handcrafted features. With handcrafted features, stochastic process regression outperformed the deterministic regression models in all three categories: intraculture, cross-culture, as well as multiculture evaluation, by significant margins. With the deep learning-based features, stochastic process regression achieved state-of-the-art performance by outperforming existing benchmarks as well as the deterministic regression models we trained in this work. Here, it is important to note that one of the deterministic regression baselines, called conditional neural process, or CNP, has the same modeling complexity as our SPR-NP model, but it does not have the stochastic latent variable. Still, the performance difference between the CNP and our SPR-NP model is pretty high. This result clearly validates our hypothesis that stochastic process regression can generalize much better than deterministic regression models, especially in the case of speech emotion recognition, where the model needs to accommodate a wide range of variations. In summary, our work studies the idea of learning distributions over functions for speech emotion recognition in order to cope with the wide range of intrinsic variations encountered in cross-cultural settings. To this end, we showed that a stochastic latent variable model based on neural processes is an efficient machine learning model for speech emotion recognition. For more implementation related details, please check out our paper. Thank you for your attention.